Hey, we're live at NASA's Goddard Space Flight Center, and we are inside of the Robotics Operations Center. If you look around, there's some of the tools and technology in here that is for robotic servicing. So we're celebrating 25 years of Hubble servicing today. 25 years ago, the first astronaut mission to the Hubble Space Telescope to service the telescope and upgrade its components launched. And we're here to talk all about it and satellite servicing, past, present, and future. So you may be wondering, what is satellite servicing? The same way you take your car in to get service, to get the tires rotated, to get the oil changed, or even just to fuel up. Sometimes our satellites in space need a little help. And that's where we've got astronauts and tools and robotics, and they all come in. I'm sure you've got a ton of questions, and I do too. Send them into the hashtag AskNASA. We're streaming live from Facebook, Twitter, Instagram, and Twitch. So start sending them on in. We've got our first guest here today. You may have heard of him. His name is Charlie Bolden. He's a Hubble astronaut, and he is also the former administrator of NASA.
Erin, how you doing? Good to be here with you.
I'm so happy to have
you
here.
Thank you. Thanks very much.
So first and foremost, can we explain to our audience why we even put satellites into space in the first place?
Yeah, I think most people are aware of the fact that we use satellites today. Everybody thinks about TV, but far more than that. We use it for disaster planning and relief. We use it to help farmers when they're trying to figure out how much to water their fields. We can get that data through satellites. Very simple things like making your Fitbit work and other kinds of stuff. That's all satellite data. And what we've done over the years is made satellites more and more capable, as you mentioned earlier in your intro, such that they do a lot of the work that we want humans to be able to do, but we don't want to put the humans at risk. So satellites and robotics devices have enabled us to get into places where if it weren't for the satellite, we'd probably have to send a human there to get the answers we want.
So Hubble was designed to be serviced, and we sent astronauts up 5 different times to do so. What exactly does a human servicing mission look like?
Well, I did not fly on one of the servicing missions. The unfortunate thing was I was the pilot on STS-31 when we left Hubble needing to be serviced, when we found out that it had this thing called a spherical aberration that caused it to need glasses like I do. And so we came up with a device called CoStar that was a big telephone booth looking set of optics that we were able to send the very first servicing crew up, remove some of the old instruments, put the new optics in, replace the solar arrays, and get it to working and seeing the way that it was intended to see when we first sent it up there. So that was the first purpose of the initial servicing mission.
And that didn't happen terribly long after it was launched, 3 years?
Yeah, it depends on how you look at it. If you look at it from the standpoint of NASA and the astronomers and astrophysicists who were waiting to get data from Hubble, it took way too long. If you're from the perspective of somebody here at Goddard who's planning all the mission, it was pretty quick. You know, trying to figure out what we needed to do, what kind of tools we needed to come up with. The good thing was we had people, you're going to talk to a couple of them, Jeff Hoffman and John Grunsfeld later, who had been with Hubble years before we first flew it and had already envisioned the kind of tools that you would need if you're going to do certain operations that are more than likely going to be needed. Changing out batteries, changing gyros, changing the solar arrays. So some of those tools were already in place. CoStar was not in anybody's plan. So, you know, the folk over here got to work And that's what took the extra time, was actually designing the new tools we were going to need, and the tactics, techniques, and procedures, if you will, that the astronauts were going to follow when they finally got to the telescope.
So you actually have a very interesting history with NASA. So you were an astronaut, and you deployed Hubble, you know, you were part of that mission, and then you were also the administrator. So tell us a little bit about your experience.
Sometimes I think the president looked back and said, who had done the worst of causing us trouble, let's let him fix them. But I was privileged to serve for almost all 8 years of President Obama's term as the NASA administrator. And during that period of time, or leading up to it actually, I had an opportunity to spend a lot of time here at Goddard, actually sit in on, be briefed on a lot of the robotic missions that we wanted to fly, things like Restore-L that are here, where we were actually going to go up and service a satellite that maybe needed to be refueled, needed to be serviced because some component wasn't working. And so we got to see quite a bit of that during my tenure as the NASA administrator. It was quite interesting and challenging.
So the last servicing mission,
I
understand that there was a maybe do, maybe don't situation. Tell us a little bit about that.
Again, it seems like I pop up in the strangest places. Right after I retired from the Marine Corps in 2003, unfortunately, the next month we had the Columbia accident, and that caused the NASA administrator at the time to cancel the Hubble servicing mission that was scheduled, and it was going to be the last planned mission. We were going to try to use robotics to service the satellite and or the observatory, and I served on a committee that actually looked at it, and the technology just wasn't there at the time. So we had to go in and talk to the NASA administrator, explain to him that the safest and surest way to save Hubble was to accept the risk of flying one more crewed mission to service Hubble, and that one, like the last two, was about as ambitious as you can get, where we had 5 days in a row of back-to-back EVAs with tremendous crews, things going wrong every once in a while, but because you had the combination of people here on the ground and the crew on board, we were able to kind of work our way through it and had 2 incredibly successful missions and left Hubble in much better shape today than I think it was ever envisioned to be by its original designers.
And then another thing that we have talked about when it comes to satellite servicing is the International Space Station, because it was quite a feat. So can you talk about like where the International Space Station falls in on the timeline of you know, the first servicing mission to Hubble and some of the evolution of servicing?
Some people will remember we were, when we did the first servicing mission to Hubble, we were looking at a space station, but there was no concept of an international space station. Actually, the International Space Station came sometime later, but what it did allow us to do when we finally made the decision with our partner agencies, and there are 5 partner agencies, including the U.S., when the decision was finally made to fly this, to build the space station, one of the side benefits of it was it gave us a platform where we could actually demonstrate some of the new technologies in robotics. For example, the robotic refueling mission, something that was a prize of the folk here at Goddard. And I understand we just launched RM3, so we have now learned how to remove caps and replace caps, to clip wires and twist wires. And now we're getting ready to actually use the mission to refuel the Landsat satellite, maybe, you know, but we're going to demonstrate that we can, in fact, transfer cryogenic material, and that'll be probably the last step that we need to demonstrate our capability of doing a completely robotic mission to service a satellite on orbit, which is something that we really want to do. The International Space Station presented the laboratory or the workshop where we could demonstrate that in space and assure ourselves that, give us very good confidence that the things we saw here in the lab really were going to work when we got them into the microgravity environment of space.
That's great, and I know we've got questions for you that are coming in, but I understand that we're going to meet up with you again later, so we're going to hold off and let people continue to send in their questions. And Charlie's got a robot demo for us later.
Well, I'm hoping that you'll spend a lot of time with John and Jeff Hoffman and let them show us the tool and maybe run over so I don't get a chance to screw up the robot. But I'm really looking forward to it. As a pilot, I didn't get an opportunity to do too much robotic operation, so I want to ply my trade down here, and I'll see you later.
All right, I'll catch you on the other side, Charlie.
All right,
thanks so
much. Thank you.
So like he said, we're going to be down there later, but send in your questions and we'll get to them throughout the show. Use the hashtag AskNASA. We're on Twitter, Facebook, Instagram, Twitch. So like Charlie also mentioned, we've got 2 of the Hubble astronauts here with us today that actually went up and serviced the telescope multiple times. We've got John Grunsfeld and we've got Jeff Hoffman here today with us. Thanks so much for being here, guys.
Well, hi, it's great to get back to Goddard. Spent a lot of happy and busy hours here getting ready for the first Hubble mission. John spent even more time.
Yep, and I always love to play with tools.
I'm sure you do. And we've got a bunch of them over here. It looks like you guys may know what to do with them, so if you don't mind showing our viewers.
Well, sure, but...
Sure. You know, you see this sign, it says ESD work area, and I don't want to shock you, but you know how you rub on a rug and then you touch the door handle and you get this spark? There's sensitive stuff back here, electronics and the tools that we don't want to break. So we're going to put on some wristbands to zap that electricity to a ground. And also, we don't want dust to get into the delicate components, so we're going to put on some smocks so we don't get everything dirty.
These are the wristbands. And
awesome. So
now, of course,
yeah.
when we were working with Hubble and the instruments, there was a lot of very, very sensitive optics. So contamination was absolutely critical. We had to put on a lot more than just these smocks. I mean, full headgear. I had a mustache at the time. John still does. That had to be covered up.
And little details you never think about. You know, for women, maybe for men too, no makeup, because that makeup could contaminate the Hubble optics.
I didn't wear any makeup. It wasn't a problem.
You didn't?
No.
You look great. So while you guys are smocking up, can you tell everybody about some of the missions that you guys were on with respect to Hubble?
I was on the very first servicing mission. You know, Charlie Bolden was on the mission that put Hubble in orbit. And then when we discovered that it couldn't focus properly, that, of course, became a real disaster. It had always been planned that every 2 or 3 years a crew would go up to service Hubble. And so we went up about 2.5 years after Hubble was launched. But at that point, the purpose of the mission was not just to put in a new instrument, which had always been in the plan, but actually to fix all of the optics. Plus, there were about a dozen other things that had broken on Hubble and had to be fixed. So it ended up being, at the time, the most complex shuttle mission that had ever been planned. And given the success of it, I think it really gave people the confidence that complex servicing tasks were possible, and I think led the way to some of the even more complex things that John and his crewmates did on some of their Hubble missions.
So which missions were you on, John?
So I was on 3 Hubble missions, the last 3 in fact. We did a mission in 1999, in 2002, and the most recent one, 2009. And amazingly, Hubble is still working great. And I think
they left it as good as new when they fixed it, really.
I think what we learned is that almost anything you can do on the ground, you know, maybe wearing, you know, these suits and gloves to protect the hardware, but anything you can do on the ground, we can learn how to do in the big bulky spacesuits. Of course, it takes us longer to get those spacesuits on than the smocks, but anything you can do on the ground, you can find a way to do it in space if you have the right tools.
So that's probably a good cue for us to go in and show the people what it is that
I checked your static out. You're good?
Give the people what they want.
We're both plugged in here. We're grounded.
Awesome. So I guess we'll start on the far side with Jeff, since you were on that first servicing mission here. Any of the tools on this table, were they used for that?
Well, this one I have fond memories of. Of course, they're all power tools. We did have manual tools, and on a few occasions we did use manual tools, but power tools, you can get the job done so much faster, and when you're on an EVA mission like this, really astronaut time outside doing useful work in a spacesuit that's the most valuable consumable that you have, and so anything you can do to speed up the process. So we do use a lot of power tools. Now this was first generation for Hubble. We would have tool carriers, and so I could plug this in. And of course, it's pretty heavy now, but it doesn't weigh anything up there. But everything has to be tethered. And of course, this has an interface that you can put long bolt drivers and little pip pins, and every one of those drivers had to have a separate tether. just managing all the tethers, it really took a lot of time. But,
yeah, but you can't afford to lose.
You can't afford to lose a tool. And boy, you know, when we were doing all the training in the pool, if your instructors saw that you hadn't done a tether properly, they'd get right on your case. The other thing that we often used, a torque limiter, which would, of course, go on the end of this, between this and the actual bolt that you were working with a telescope. And the reason for that is you want to just put the bolt in with enough force that it won't come out, but you don't want to overdrive it so that it might get stuck, or worst case, you could actually fracture the bolt, in which case you're never going to get it out. So we were very careful. For every job we had, there would be an indication in the checklist, you know, set your torque limiter to such and such a level, and then...
Of course, torque is how hard you turn something.
Right, and then also, you know, 19 turns clockwise, and just to let the people...
Not 20, not 18.
And we would actually count them out. You know, I'd be there, you know, doing the thing, and, you know, it's 1, 2, and so on. That so that the people on the ground could really follow what we were doing, and that was critical. But then, of course, this was the first generation, and when you guys went up, you had some more developments.
And that's one of the features of the Hubble program at large, is as astronauts, we got to work on a daily basis with engineers and exchange ideas and try things. Some things worked, some things didn't. And so this is the astronaut death ray laser. No, this is a power tool that's the next generation. And this may look a little more like a power screwdriver that you might have at home, and it incorporates the features and lessons learned.
This was the big battery for this, and here you're all built in.
Battery's now in here, the torque limiter's in here, and this has electronics that counts all the turns and tells you what they are, records what was torqued, and so this is now the standard work tool for astronauts in space. Now it's pretty heavy here, but in space everything floats, so it's nice. This is a tool that's used on virtually every International Space Station spacewalk, and so what we developed for Hubble is now used across the space program, but it doesn't necessarily work for everything. You know, this was still too big and didn't have the capabilities we needed for some other repairs that we did on the last mission. I had to remove a lot of tiny screws in space. And what do you need to remove tiny screws in space? Well, you need a tiny screwdriver.
Tiny screwdriver, yeah.
Right.
We had that problem on the first mission with our final EVA task on the solar ray drive unit, where we had little 2mm screws that we just couldn't use this for it. It was too big.
So we developed what's called the mini power tool. Now it's not that mini, but it's a lot smaller than these others. And so we have an evolution of tools through time that allowed us to do the repairs. You know, we all think about these amazing Hubble images. Yeah. Jeff and I are both astronomers, and so we love the science. We wouldn't have any of that unless on the first servicing mission they'd repaired the optics and put new instruments in. Yeah, and on every mission we put new instruments in.
And of course, every new mission we would build on the capabilities that had been demonstrated on the previous mission, so that you know, by the time you got to the final mission, which I think you're going to talk about this ACS, but you did things that had people suggested that they could have been done at the first servicing mission, they'd have gotten kicked out of the room. It's, you know, that's just way beyond scope of what anybody can do. But we did it.
Yep. Typically, if an instrument failed, we'd bring up a whole new instrument the size of a big bulky refrigerator. On the last mission, we couldn't do that. We brought up one new instrument, but we had two that were failed, and we were able actually to repair it with a bunch of very special tools that allowed us to, you know, this tool allowed us to cut a metal plate, to remove all those tiny screws.
Without having them float away.
Right. We used a specialized piece of equipment that kept the screws attached so that we could remove all those screws, get a metal plate off. Maybe I can get the plate off, maybe not.
Do you have any fingernails?
I have very small fingernails. We can always turn it over.
Okay.
Can't do that in space.
You could not do that in space. I was thinking the same thing.
Inside were 4 circuit cards, and we were able to pull those out. Now,
so,
this
I mean,
is something
the idea of being able to work on the level of removing and replacing circuit boards, it would have been unthinkable when people first started to think about what astronauts could do in servicing. But as we gradually got more confidence, one mission after the other, you actually did it.
And each mission we did try things that folks said, no, you can't do that. We would go do it. And so this is sort of state of the art for people in space now. And something that I think in the realm of today, you know, you really need the human dexterity to do. But I think a lot of the tasks that we did, removing the large bulky objects, today we could do that with robots.
Probably could. Our robots have gotten a lot more sophisticated, and of course they're working on robotic servicing here at Goddard now for, this is the Landsat, and refuel it. And you know, frankly, I mean, I love putting on a spacesuit and going outside, but if there's something that can be done by a robot, we ought to let robots do it. Design the servicing for robots, and then if you run into problems that the robots can't handle, you've got a simpler interface for the people who have to actually go and do it.
And if you look at the robotic tools, they look kind of like evolutionary tools from the hand tools that we use. They're just built into the hand of the robot. So I'm really excited about that development.
I mean, the idea of being able to recycle satellites and to improve the capabilities, which is what we've done with Hubble, it's been a game changer for Hubble. And hopefully as we go into the future in the latter part of the 21st century, that's going to be standard operating procedure. It's so much more efficient.
Makes a lot of sense. And of course, as we go out and explore planets, Mars, you're going to want robots out exploring before we can get there, even when we're there. And you'll need robots to repair the robots. So.
That was awesome. Thank you so much for sharing those tools. And we've got a bunch of questions coming in from social media. I know you're sending them in on Facebook and Instagram and Twitter and Twitch, and we've got some good ones. So Jeff, the first question I have for you was, what was the experience kind of emotionally of being on the first servicing mission?
Of course, everybody knew how critical this situation was. And as an astronomer, I had lots of astronomer friends who would call us up and say, you know, can NASA really fix this? You know, people who had devoted large parts of their career to Hubble. So, you know, first of all, it was really exciting being put on the crew. This was a primo mission. Everybody knew how important it was. And then, you know, as an astronomer and an astronaut, and you must have had this, you know, to be able to put our two hands on the greatest telescope in the world, up in space. I mean, you know, that's something I'll never forget. That's a life.
I think I saw your handprints on the Hubble.
Well,
but I did have a similar experience. You know, we got up to Hubble, and it was my third space flight, but my first spacewalk. You had already done a spacewalk.
Yeah.
And I was on the robotic arm, and I was being moved back towards the Hubble, and there was just a moment there, you know, which is the pinch me moment, where I reached out with a finger. Now, of course, I'm wearing a glove in a spacesuit, but I reached out with a finger and touched the Hubble just to make sure it was all real.
Yeah, I mean, it's a beautiful telescope. That it's covered with reflective material that reflects the colors of the Earth below it, and I mean, for those of us who got to play a part in the history of the Hubble Space Telescope, I think for all of us, it was a highlight of our careers.
That's great. We've got one more question, and I'll send it over to John. So you did it 3 times, but how long does it take to get to Hubble?
Well, that's a great question, because launching from planet Earth to get to Earth orbit only takes 8.5 minutes. Kind of a rough ride, but once you get there, it took us a couple of days to reconfigure the shuttle and to chase down Hubble, so that on the 3rd day, we grabbed the Hubble with the robotic arm of the shuttle and put it into the payload bay so we could work on it. So it takes about 3 days. And then on day 4, we started the spacewalks.
They keep you busy up there.
Yep. Oh, it's a very busy
And it's
timeline.
exciting when you're doing that rendezvous. You know, when you get your first glimpse of the telescope, and it's just a little point of light, and then every orbit you get a little bit closer, and then you can start to see its form, and it gets bigger. And when it finally gets close to you, it's big. You know, 50 feet from top to bottom, and it's just really exciting.
Thank you guys so much for being here. So everybody, if you just tuned in, we have Hubble astronauts. We got Jeff Hoffman, we got John Grunsfeld talking about Hubble tools. Thank you so much both.
Our
for
pleasure.
Being here and taking
We love
the
it.
time
It's
today.
been fun, real nostalgia getting to pick these things up again. Wish I could take it into space, but we'll leave that for the younger guys, I guess.
We'll work on that. We'll see what we can do. We'll phone a friend. So we're here in the robotics, area for Goddard, and we talked about Hubble and we talked about servicing and we talked about humans, but now we're ready to talk about the future and what servicing may look like from here on out. And to do that, we've got the folks who actually work on some of these instruments that you're seeing in here. And today with me, I've got Ben Reed from Satellite Servicing. Thanks so much for being here, Ben.
Of course.
So let's talk about robotic servicing. What are the advantages of using robots?
So the advantages of using robots is the same as using robots here on the ground. We like to use them in places, the traditional three that people like to say is dumb, dirty, and dangerous. So let's focus on the dangerous. Astronauts are absolutely fabulous. I love the astronaut corps. Unfortunately, we don't have the technology to protect astronauts from radiation in, for example, polar orbit around the north and south pole of the Earth. Radiation is worse there than it is at the lower latitudes. As a result, we can't work on missions sending astronauts to polar orbit. It wouldn't be good for their health, so we're not considering it. But that is a ripe opportunity to develop robotic technology, because there are a lot of satellites in low Earth orbit, polar, LEO polar. In fact, one satellite that has been there since 1999 is a satellite called Landsat 7, and you've been looking at part of it in this feed. What you see here is a full-scale mock-up of Landsat 7, about 22 feet long, and we're not considering sending astronauts to work on a satellite in that location because of the environment. So that is a perfect opportunity to develop robotic technology to be able to service a satellite like Landsat 7. So we absolutely do not view it as robots or astronauts. Each are unique, each have capabilities that the other cannot duplicate. We use them for different jobs.
Awesome. So here in the Robotics Operations Center, you've got a couple different of ways that you simulate being in space. Can you explain to our audience what some of those ways are?
Sure. So we have a vacuum chamber down the hall in this complex here at Goddard Space Flight Center, and that's where we simulate the vacuum of space. In this room, we need to simulate other aspects of space. So what is another aspect? It's dark. If the sun's not shining on you because you're on the night side of Earth, space is very, very, very dark, as you all know when you go outside at night. So that is why you see all these black curtains everywhere, is we need to simulate a robot working on a satellite in the absence of light. So we do lights out testing in this laboratory. We kill all the lights, and if you look at below the mock-up of Landsat 7, these lights that you see there, that is the exact same lighting that we would use during a robotic servicing mission of Landsat 7, illuminating the work site just as it would be illuminated in space. So that's one aspect of how we simulate space. A more difficult aspect of space that we need to simulate so that we can be testing in as realistic an environment as possible is gravity. Now, it is very difficult to turn off gravity. In fact, no one knows how. But we can simulate no gravity by a robotic platform that can move objects around as if they were floating in space. And let me show you what ours looks like. So come with me this way, Erin.
I'm with you.
All right. So first, let me back up a half a step and point out the fact that every satellite in space, at one point or another, was blasted up by a rocket. So you could imagine a rocket and a satellite. You need to attach the two together so the satellite doesn't fall off during launch. And how they're attached to each other is done with what's called a Marmon ring. And so what we have here is the lower end of a satellite, and here is the Marmon ring. So this big ring here is the Marmon ring. We have this satellite mock-up on this hydraulic Stewart platform that we call a hexapod, 6 struts, hexapod. We have a robot in front of it, and the robot would reach out and touch it, and it needs to react. It needs to bounce off and float away as if it were in space. So we have developed a very sophisticated technique to simulate space contact dynamics to put a satellite in motion. And so I'm going to shout across to a fabulous engineer, Brian Gregory, and he is going to put this satellite into motion. Take it away, Brian. 5 miles away. Didn't answer her phone. I called 3. So, it's not often that you get to see space simulated in Greenbelt, Maryland, but it actually is a common occurrence that right here at Goddard Space Flight Center, we simulate space on the ground in our robotics lab.
Very cool. That's awesome. I can't imagine that out in space now. Black and the
That's right.
lights. So humans, obviously, in this facility have developed this types of technology. So the human and the technology, and you see the horror films, human versus robot. But really, when they come together, they create amazing things. Can you tell us a little bit about that interaction between humans and robotics and how it makes such a successful product?
Oh, that's an excellent observation. So going back to the Hubble missions, in every Hubble servicing mission, we had humans and robots working together. We have trained, incredibly brilliant, fantastically dexterous astronauts working in the shuttle payload bay with a robotic arm. The shuttle had a robotic arm in the payload bay, and they would work with that arm in maneuvering the objects around that they were placed inside Hubble. Today, as we think about robots going into, for example, LEO Polar to work on satellites like Landsat 7, we are going to keep the astronauts or the humans on the ground, and they will remotely control the robot from the safety of planet Earth with the robotic arms being in space. And I can show you that in the back of the lab. So if you'll come with me, Aaron. And while we're walking, I will point out as we walk across the lab, you can see on International Space Station, which is what these video feeds are of, robotic arms on International Space Station. So NASA has a long history, robotic arms on the shuttle, robotic arms on space station, robotic arms on the surface of Mars. And I'm going to show you the latest generation of robotic arm right behind this wall of monitors.
Getting close, getting close.
All right. So here we are in the next part of our tour with our space arm and our 2 robotic arm operators, Joe Easley and Charlie Bolden, who you've already met. So this robotic arm is flight-like. So what does that mean? It has got similar materials, finish, electronics that can all withstand the rigors of space. So this flight-like robotic arm, Joe and Charlie are going to go ahead and put it into motion.
Okay, and I'm just...
It's a 7-degree of freedom arm, and what the heck does that mean? What that means is the shoulder, elbow, and wrist have 7 articulating joints. So 3 at the shoulder, you see it's doing a shoulder roll right now. It's got 2 at the elbow and 2 at the wrist. So 3 plus 2 plus 2, yes, that's NASA arithmetic for you. That is 7. And you see they are changing the orientation of the end effector to point right at us. So with 2 different hand controllers, astronaut, retired Marine Corps General Charlie Bolden is controlling this 7-degree of freedom arm, pointing it right at the camera. So it is it's at this very robotic control station that we will be manipulating robots in the future to perform servicing operations like refueling on multi-billion-dollar assets in space, extending their life, getting more value out of the taxpayers' investments with this technology.
That is amazing. Thank you so much for showing us your toys, and thanks, Charlie, for volunteering to play. We've got a bunch of questions.
Thank Joe.
And thanks, Joe.
Come on.
Skilled but natural over here.
Thank you for teaching Charlie everything he knows about robotics.
Very true. Very true.
Definitely not.
So like I said before, we've got questions coming in from social media, and I've got some for both of our friends over here. So let's start with Ben. So what other satellites are designed to be serviced in space by robots?
That's an excellent question. So designed to be serviced, there's really only two: Hubble and the International Space Station, both designed with human servicing in mind. So those are very notable satellites. If we went to the local grocery store and asked the average shopper, name me two satellites, probably those would be the two that they would say, Hubble and the ISS. But there's 1,800 other satellites operating in space as we speak right now today. 1,800 thereabouts, two of which were designed to be serviced. So a technique, a capability that we are actively working on with the hardware here in this lab is the ability to service a satellite that wasn't designed with servicing in mind, the 99%, not just the 1%. That's very much within our active program design here, is to work on technologies and capabilities for the many, not just the few.
Okay, and Charlie, I know I left you out of the question thing earlier, but we've got a bunch of them that have come in for you now. So from Instagram, we have someone asking how long Hubble is projected to be in service.
Ooh, that's a good question. And you asked me, I would say, I think I don't know what we're talking about now in terms of the finite end of it, but Hubble's in great shape. Every time we have a problem, it takes itself into safe mode until we can figure out what's wrong, and then we bring it back out again. I don't think anybody would venture, I will not venture to take a guess as to when Hubble's life will be over. The final decision will probably be made by the budget guys, I hate to say, because once we have James Webb in place and operating, it was intended to be the replacement for Hubble. My guess is you're going to see the budget guys and the astrophysicists and the astronomers go at it, because Hubble will continue to give us data that we can use to feed into telescopes like James Webb to make them even more efficient. So I would say Hubble's got a lot more life than we're probably going to give it, to be quite honest.
And you mentioned something really interesting. So there are things that we can do from the ground, not with astronauts or with robots, to extend the life of Hubble. What is that?
Well, I wasn't saying we could do anything to extend the life of Hubble, but what I was saying before was the way we left it after the final servicing mission, it was in much better shape than it was designed to be when it was built. So it's a much more capable observatory today than anybody ever imagined it would be. And that's why I think there's probably somebody in this building who will venture a guess as to Hubble's lifetime. I'm not one of them, because it's not the same observatory that we designed and built back in the 70s, 80s, and 90s. So I think it has more capability than we can imagine. Ben, you may know.
Well, there is a phrase we use with all complex equipment, Hubble being one, infant mortality. Yep. Infant mortality bit Hubble in a couple of different ways. Solar array had some issues. Gyros had some issues. The optics, of course, we discovered it had some unique features with the optics that weren't exactly by design. Hubble, one of the few exceptions where we have, through servicing missions and through smart engineers on the ground, overcome that infant mortality, and now it's going like gangbusters. I have to agree 100% with Charlie. It is far more powerful than the day it launched. In fact, I believe the number is 4 orders of magnitude more powerful than the day it launched, because Moore's law advances technology here on the ground. No different with the cameras that were put in by these very capable astronauts. So It's far better than the day it was launched, and knock on wood, we're going to keep the science discoveries coming.
I've got one more specific question for Ben. So are there applications for these technologies, like the robotic arm, beyond satellite servicing?
Sure. We want to discover our place in the universe. And one way to do that is to go to planetary bodies, comets, asteroids, surface of the moon, the surface of Mars, and collect samples. Collecting samples and analyzing them when we are there, as Mars Curiosity rover is doing. We flew the chemistry lab to the surface of Mars. That required a lot of work, and that was an incredible achievement. But just think what we could do if we could bring a sample back from the surface of Mars or an asteroid or a comet back to Earth, like a big sample, not a few grains, which we've already done from a comet. So the ability to have advanced robotics, to have these tremendous capabilities that engineers like Joe are helping us develop, and use those for other exploration missions to help support astronauts going further into the solar system. We are absolutely focusing on that as part of our mission set, not just satellites. Even though that's a broad thing to say, we're looking at the entire spectrum.
Aaron, a good example of what Ben was just talking about is we have a mission that just accomplished one of its major milestones, and it got kind of lost because it came right on the heels of InSight's landing.
Yeah.
It's called OSIRIS-REx, that is now orbiting Bennu, an asteroid, and that's exactly what Ben was talking about. It's no humans involved whatsoever. It's surveying to find a place that it can land, so to speak, go down, get a sample, and then bring it back. And for the first time, we'll actually have a sample of soil, if you will, from an asteroid that's going to help us understand more about our solar system and more about our own planet Earth, since it all started from the same place. So, the stuff that Joe and the guys here are doing with the satellites that they're working on right now, I would not even venture to say what it is that we cannot do with satellites and robotic spacecraft.
I love that. So I know that the astronauts kind of answered it from their perspective, but from your perspective, what lessons from Hubble did you incorporate into the servicing technology that you're working on right now?
Oh, that's a great question. I'll give you the general answer and then a specific answer. So the general answer is Hubble has been in orbit for many years. When we got to Hubble, there were items on it that weren't exactly like they were when we left it, especially on the outside. Space is an incredibly harsh environment. Radiation, micrometeoroids, orbital debris, solar thermal cycling. It takes its toll on the outside of the telescope. Every telescope or every satellite faces these challenges. So what we did with Hubble, we designed our tools and our techniques and trained the astronauts to accommodate a wide range of conditions when you arrive. And one thing technique we used was, if you're not sure the condition of a component, what it's going to be, bring up your own replacement. That way you can be sure that what you leave behind is pristine or will work properly. So, robotic servicing. We are going to be going to a 22-year-old satellite, so it'll be old enough to drink when we go to refuel it. It has blanketing on the outside, that shiny gold blanketing you saw earlier. We don't know if we're going to mess up the blanketing when we robotically cut a hole in it to get access to the fueling valve. So what are we going to do? We are going to bring up our own thermal cover in case that blanket gets mangled, and quite frankly, we are learning by doing. We might make a mistake. By bringing our own thermal cover, a 5-sided top hat, so to speak, we will be sure we can leave that satellite in a stable configuration, thermally stable configuration, with our own thermal cover. So there is an example of what we learned with Hubble was, if you can't trust it, bring your own. We're going to do that with robots as well.
And so unfortunately, we've only got time for one more question. How are humans also involved in the robotic servicing that we're seeing here in this lab? What is the human component here?
Human judgment, human dexterity, human skill.
You got it.
Guys like Joe here, running those hand controllers, right? He is going to be doing that with video coming back down from our tools. All of our robotic tools have cameras on them. So Joe is going to be using those camera views coming back on his screens here and deciding how much to move the joystick in what direction. So robots are not smart. They are not smart at all. Guys like Joe are smart, they've got judgment, they've got experience, and that is how we are going to make sure that the best qualities of humans and the best qualities of robots are married together in these future missions.
Now you just made it really hard for Joe to get around the lab the rest of the afternoon.
Everybody will get out of your way, Joe. Get out of my way.
Everything for Joe. Thank you all so much for being here and for answering all these questions and for giving us this wonderful demo and this space to host this show. We're very grateful, but the party's not over yet. We've got 2 more live shows tomorrow with astronauts. We've got 2 astronauts from Servicing Mission 1 talking about their experience on the first ever human servicing mission to Hubble. How did that go? Find out tomorrow on Facebook, our Facebook specifically. And then we also have a show in the afternoon of astronauts from all the 5 servicing missions, plus we got Charlie will be with us too. So you're going to want to tune in, you're going to want to send in your questions, and we will see you then. But in the meantime, if you want more Hubble, you can always find us on nasa.gov/Hubble or on social media at NASA Hubble. Thank you guys again so much for tuning in.
Five, 4, 3, 2, 1, and liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe. About humanity's quest for knowledge. The only way of finding the limits of the possible is by going beyond them into the impossible. I want to wish Hubble its own set of adventures that it may unlock further mysteries of the universe.
Hubble Space Telescope Imaging Spectrograph, or STIS, has capabilities like searching for black holes and looking at the atmospheres of planets orbiting other stars. After STIS had a power failure in 2004, the Hubble team was tasked with replacing STIS's damaged electronics boards on the final servicing mission in 2009, which would turn out to be a memorable day for everyone involved.
So for about 2 years, I spent almost every day with the EVA team, 4 crew members.
We practiced that repair many, many times, and we had practiced it in the water, start to finish, in the pool many times.
We spent hours and days and weeks and months going through what if this bolt fails? What if the cable doesn't mate? So I felt that we had covered, as much as we could have thought of going into this EVA.
So we came in to work here at the Space Telescope Operations Control Center at Goddard.
Our mechanical response team was watching the EVA in a conference room in Building 29.
I was located down at Johnson Space Center along with the servicing mission manager.
The day started out really well. I was trying to make it a perfect day, no problems.
So they get to the section where they have to remove the handrail on STIS. And you have to remove this handrail that was designed actually to help remove and install the entire instrument. in order to access the electronics board underneath.
And we watched Mike Massimino attempt to do a rather simple task. All he had to do was remove 4 screws from a handrail.
And so the 2 screws at the top of the handrail came off fine. The one on the bottom left comes out fine. I go to the bottom right.
We could see the pistol grip tool spinning in the bolt head, and the bolt wasn't coming out.
I don't want to strip the thing.
Oh my God. That was the first thing, you know, it's what are we going to do? Because this is a showstopper right here.
For a while, probably about an hour or so, we were trying different bits on the end of the power tool. You know, we were trying all kinds of things.
You know, and one thing that crossed my mind was, what would you do? What would you do at home? You know, what would you do in your garage? You know, and I was thinking back to my garage, you know, and sometimes what would I do, you know, and I just kind of, you know, use the brute force, you know, so I thought, you know, what about just trying to break it?
It didn't even occur to a lot of us, just because it's something that you're not really ever trained to do or think of.
So one of the things I did was I called back to James Cooper back here at Goddard.
James Cooper called us on the speakerphone and said, "Hey guys, you're watching this, right?" And we said, yeah, of course.
We found out we did have a mock-up of the STIS front panel with the handrail on it.
We came up with a quick plan. Bill Mitchell said, I've got 2 handrails inside the clean room, and Ken Dickinson and I came up with a plan for how to rig up the test. So we scattered into the building to get all the materials we were going to need. Well, it was a Sunday, nobody was around, so I'm literally running through the halls, and I run to where the techs would be, and I find a guy, Gene McAllister, who happened to be in the building working on another project. So he said, "What do you need?" He seemed to pick up on my body language before I even asked my question. I told him I need a torque wrench and I need a digital fish scale. He takes off to go get it. I go to 190. Ken Dickinson's already in there, and within minutes, Bill Mitchell comes busting through the door, carrying the handrail, still in his bunny suit and his cleanroom garment. We get the handrail all set up. Everything's ready to go. We text a couple pictures back and forth. James gives us the green light, and Gene stands up on the table and starts pulling the handrail. And right when he got to 60 pounds, it snapped. Actually, the bolt went flying.
Once we'd done that test, then I got on our communication loops and called it to Jim Corbo.
So ultimately, you know, James came back and said, you know, it'll take about 60 pounds of force for them to break it off.
So Goddard had done this test, fed the information to us. We talked to the flight director about it to get him comfortable.
Okay, Mass, you copy that. 60 pounds linear at the top of the handrail to bust off that bottom bolt. I think you've got that in you. I can try.
I knew I could do that.
What if he pulls it off and there's debris? What if he pulls off the handrail and there's a sharp edge? What if it takes a lot of force and it comes back and hits him?
Mike Massimino was able to put some tape over the head of the bolt to contain debris that might go flying.
And so I taped it as best I could, and Boyner was with me, helping me to tape that thing. And then
Planet Houston, we don't have video right now, but we're ready. Okay, Mass, you have a go. Here we go. Stop. Disposal bag, please.
Everyone erupted in cheers because when he pulled it off, he didn't see any debris, and he knew not to touch the potential sharp edges, and then we could just put that fastener capture plate on and complete the STIS task.
the rest of the repair went fairly well. STIS, I mean, it was fine actually, and STIS is working.
That 1 or 2 hours that I worked on breaking the handrail, that task, that very well could go down as a highlight of my career.
So the Goddard team did a great job, and I'm forever in their debt.
We are all explorers. It's in our DNA. We explore the depths of our oceans, our planet's inner regions, and its desolate outposts. We never stop exploring. Galileo opened our eyes to the heavens with his use of a newly invented instrument, the telescope. He started an exploration renaissance of the sky that would take us to the moon and beyond. For over a quarter century, the Hubble Space Telescope has been unlocking the mysteries of the universe. allowing us to explore the edges of space and time. From nebulas to galaxies, from newborn stars to planet formation, from exoplanets to our own planets, and from dark matter to dark energy. Hubble has allowed us to see the breathtaking details of the universe never before seen. We salute the thousands of men and women from around the world and in space that have given humanity this incredible exploration machine, while we celebrate its past and dream of its future discoveries. The Hubble Space Telescope, inspiring the explorer in all of us.
Engineers at the Goddard Space Flight Center discovered that there was a very small fault in the power control unit.
You know, it's the heart of Hubble. All the power runs through that box.
To change out the PCU, you actually have to turn off the telescope. And this is something we've never, ever done, is turn the telescope completely off.
Because when you turn all of the power off of Hubble, it starts getting cold.
You know, space is a cruel environment, and so the temperature control of the telescope is very important.
I was brought on to develop a command procedure which we called the SuperProc, which would turn the telescope off as quickly as we possibly could.
For months, we analyzed different scenarios.
We thought through everything that could possibly go wrong.
You know, we felt confident. We had a ream of analysis.
I arrived late at night for the start of the orbit shift.
So the team was very prepared and very focused on what we had to do that night.
You know, everything was pretty calm. Everything was, you know, you're nervous, but everything was going according to plan.
John is getting into the suit, he's getting into the airlock, they're going through all their checklists, and we're sending commands and commands. And it's like we're starting down a roller coaster ride.
The goal was always to have the work site ready to go with whatever power needed to be removed for safety considerations just when the crew got to the work site.
All of a sudden, we hear over the loops, we hear John say, "I have a leak."
What does that mean? A water leak in a suit, you know, that's not good.
Then Al comes on the loops and tells us, stop doing the commanding. We need to figure out what we're going to do from this point.
What we immediately did was started to assess what components we had already powered off.
Then I said, you know, these things don't have a lot of margin. You know, we're up to the line.
Our thermal engineers would tell us, well, given the condition and the current temperatures, we've got a certain amount of time.
I said, okay, turn on this instrument, turn on these, you know, general bus heaters.
At the same time, the astronauts are frantically working to change out John's suit to get him back ready.
The next thing we hear is, okay, we've got it fixed.
You know, he got into a different suit and things, you know, were working well. We turned right back around and started shutting things back off.
And so we were right back on that roller coaster of powering down again.
It was a relief to me. We're back on track. You know, we're back to, you know, the original plan.
Luckily, we had everything reconfigured in time, so by the time John got to the door and was ready to start working on the PCU, we were able to send the SuperProc.
The telescope is powered down. Tell those SuperProc people they're geniuses.
The telescope was completely off.
It's an engineer's lifeblood to sit there and watch the telemetry, to watch the temperatures, watch the voltages, watch the power, make sure everything is safe while they're working on the telescope, but we had none of that.
All we could do was sit back and watch John perform what was, you know, the most amazing EVA of all time. It was like watching poetry in motion.
Before we knew it, it was time to power things back on.
They give us the call down to say, go for the PCU aliveness test. This is where we actually can send the commands to turn the telescope back on.
All of a sudden, this flood of telemetry starts coming in from the telescope.
Power was running through it, the batteries were charging, and for me, the temperatures were looking in a safe, range.
Everyone's looking at their screens, and it was pretty much just green across the board.
Hubble is back alive.
We were very pleased, of course.
It was a lot of work. It was years of work, so it wasn't, it wasn't wasted. Everything worked out according to plan.
Hubble is a great project with amazing people, and we were able to prove it that day.
InSight is now traveling at a velocity of 2,000 meters per second.
Our InSight mission arrives at Mars, announcing the companies that will help us get to the moon, and the space station's next crew wraps up pre-launch activities. A few of the stories to tell you about this week at NASA.
Touchdown confirmed.
That confirmation at 11:52 a.m. Pacific Standard Time on November 26th that our InSight lander survived the plunge through Mars's atmosphere and was safely on the Martian surface triggered waves of relief and elation from InSight team members at our Jet Propulsion Laboratory in Pasadena, California. Like past landings on Mars, this one was expected to be extremely hard and not without peril. So no surprise that crowds braved the rain in New York City to watch outside the NASDAQ stock market. While inside, the mission was recognized during the closing bell. Even the crew aboard the International Space Station paid close attention. When the dust settled, this photo from the lander, showing the surrounding Elysium Planitia region, erased any lingering doubt the mission had indeed struck a nearly flawless landing.
Today was a great day for the United States of America. It was also a great day for our international partners. This was seen all around the world.
Kudos for pulling that one off, and we are looking forward to what the data comes out of this mission.
InSight will be the first mission to study the deep interior of Mars, which is expected to help us learn more about how Mars and other rocky celestial bodies formed, including Earth and our moon. The mission could teach us valuable science as we prepare for our next bold endeavor to send astronauts to the moon and later to Mars.
The history books will be rewritten about the interior of Mars. And these first couple of pictures of a place no human has ever seen before also remind us that in order to do science, we have to be bold and we have to be explorers.
Also a success was our Mars Cube 1 or MARCO experimental CubeSats that launched with InSight as a communications technology demonstration. The first CubeSats sent into deep space not only helped relay InSight's landing signal and surface photo back to Earth, but even captured an incredible image of Mars as they flew by the red planet. With landing complete, the InSight team will focus mainly on preparing to set the lander's instruments on the Martian ground. InSight is expected to start collecting science data within its first week. On November 29th, we invited media to our headquarters in Washington, D.C. for the announcement of new moon partnerships with U.S. companies. Working with American companies is the next step to achieving long-term scientific study and human exploration of the moon and Mars.
We want multiple providers that are competing on cost and innovation so that we as NASA can do more than we've ever been able to do before and advance the human spirit.
Under Space Policy Directive 1, The agency will lead an innovative